Modern knives are engineered to fail. Medieval blades were forged to endure. This is the story of a metallurgical secret so powerful that industrial steel manufacturers spent a century trying to bury it, and why a 900-year-old sword can still outperform every kitchen knife in your home. Chapter 1. The catastrophic failure of modern steel. Your kitchen knife is a lie, not a bad product, a deliberate deception. The blade you bought last year, marketed as professional grade or surgical steel, will be dull and chipped within 18 months. This isn't accidental wear. It's engineered obsolescence. Modern steel manufacturers discovered something dark in the 1,960 seconds. If they made knives that never needed replacement, they'd destroy their own market. So they optimized for initial sharpness and abandoned durability entirely. The result is a global steel industry, producing billions of blades designed to fail. Meanwhile, in the British Museum's medieval collection, a 12th century English sea axe, a single-edged utility knife, still holds an edge sharp enough to shave paper. It's been in storage for 800 years. No maintenance, no sharpening, just sitting in a climate-controlled case, waiting to prove modern metallurgy is a regression, not progress. The curators won't let researchers test it on anything harder than paper they're afraid of. Damaging the testing equipment, not the blade. In 2015, a team from the University of Cambridge Material Science Department analyzed the CX using non-destructive electron microscopy. What they found rewrote everything we thought we knew about steel. The blade's edge contained a microstructure that modern mills cannot reproduce. Not choose not to, cannot. The medieval forging process created a crystalline lattice at the molecular level that our contemporary techniques physically destroy. We've spent 150 years perfecting metallurgy, and somewhere along the way, we forgot how to make steel that lasts. Chapter 2. The smoke and thunder of the forge. Close your eyes and smell it. Charcoal, smoke thick enough to taste, mixed with the acrid tang of heated iron and the sharp bite of quenching oil. This is the sensory world of the medieval forge, where metallurgy happened through observation, not theory. The blacksmith's hands, calloused and scarred, read temperature through color, a skill so precise that modern pyrometers often prove less accurate. Cherry red meant 730 degrees Celsius, perfect for shaping. Orange yellow meant 1,100 degrees Celsius, the threshold where iron becomes steel through carbon absorption. White heat meant disaster, the metal burning, its structure ruined. No thermometer could teach this. Only thousands of hours watching metal glow, feeling its resistance under the hammer, hearing the tone change as crystalline structure shifted. The greatest medieval smiths worked in near darkness, the better to read the subtle color shifts in heating metal. They understood something fundamental. Metallurgy is a conversation between human and material, and you can't hear what the metal is telling you if you rely on instruments instead of senses. The forging process began with bloom, iron, spongy, impure metal extracted from ore in a charcoal furnace. Modern steel comes from blast furnaces producing homogeneous alloys. Medieval smiths worked with inconsistent material, full of slag inclusions and varying carbon content. This should have produced inferior blades. Instead, it produced superior ones. The secret lay in what happened next. Chapter 3. The pattern that changed everything. Pattern welding. The term sounds decorative. Aesthetic museums describe it that way. But pattern welding wasn't art. It was survival engineering. Medieval smiths discovered that if you took multiple strips of bloom iron with different carbon contents, stacked them, heated them to welding temperature, and hammer forged them into a single bar, something extraordinary happened. The varying carbon layers created a composite structure with properties no single steel could match. High carbon layers provided hardness and edge retention. Low carbon layers provided flexibility and shock absorption. The boundary zones between layers, microscopically thin transition regions, acted as crack arresters, preventing fracture propagation. A pattern-welded blade didn't just resist breaking, it was structurally incapable of catastrophic failure. Modern materials science has a term for this: fiber-reinforced composite engineering. It's the same principle used in carbon fiber, in fiberglass, in the Boeing 787's fuselage. We invented it in the 1960 seconds and act like it's revolutionary technology. Medieval smiths were doing it in the year 800. The National Museum of Denmark houses a 9th century Viking sword that was pattern-welded from 15 separate iron bars, folded and forged together through 180 hours of continuous work. Metallographic analysis revealed 32 distinct layers in the final blade, each between 0.3 and 0.7 millimeters thick. The precision is inhuman. No modern blacksmith has successfully replicated it. Some have tried experimental archaeologists attempting to recreate Viking swords using period-accurate techniques. Every attempt produces blades that look correct but perform worse than the originals. We're missing something. Some tactile knowledge, some understanding of how carbon migrates through iron at welding temperature, some awareness of grain structure that can't be learned from textbooks. Chapter 4. The Alchemy of Edge Geometry. But the composite structure was only half the secret. The other half was edge geometry. And this is where medieval bladesmithing becomes almost supernatural. Modern knives use a simple V-edge, two bevels meeting at an angle, typically 20-30 degrees. It's easy to manufacture, easy to sharpen, and terrible for edge retention. The acute angle means minimal steel supporting the cutting edge. Under stress, that thin edge deforms, chips, or rolls. Medieval blades used something different: a convex edge, called an appleseed or moran edge in modern knife-making communities. Instead of two flat bevels, the blade transitions from thick spine to sharp edge through a smooth, continuous curve. This geometry does something remarkable. It places the maximum amount of steel directly behind the cutting edge, supporting it under stress while maintaining an acute cutting angle. The physics seems contradictory. How can you have both a thick, strong edge and a thin, sharp cutting surface? The answer is three-dimensional geometry. A convex edge presents a thin profile to the material being cut, but that thin profile is supported by exponentially more mass than a V-edge. Imagine pushing a wedge into wood versus pushing a barrel-shaped object. The wedge penetrates easily, but splits the wood. The barrel compresses the wood without splitting because the force is distributed across a curved surface. Medieval blades worked on this principle. They didn't split material, they separated it. The University of Göttingen's engineering department tested replica medieval knife edges against modern V-edges in 2018. They used standardized cutting tests: rope, leather, green wood, and bone materials medieval blades would have encountered daily. The results were embarrassing for modern design. Medieval-style convex edges maintained sharpness for 400% longer than modern edges. When they finally dulled, they dulled, gradually becoming less sharp, but remaining functional. Modern V-edges failed catastrophically, working perfectly, then suddenly chipping or rolling, becoming useless. The medieval design failed gracefully. The modern design failed absolutely. Chapter 5. The quench that defines destiny. Now, the blade is forged, shaped, ground to its final geometry. It's still soft, workable iron that would bend under stress. The next step transforms it from metal into legend, the quench. In the dim light of the forge, the smith heats the blade one final time, not to welding heat that would destroy the careful layering, to critical temperature, 700–800 degrees Celsius, where iron's crystalline structure becomes fluid, ready to lock into new configurations. The color is deep red, barely glowing. The moment must be perfect. Too hot, and the blade will crack from thermal shock. Too cool, and the steel won't harden. The smith has perhaps 3 seconds to make the decision. Then, With a motion practiced 10,000 times, the blade plunges into liquid. Not water too violent, it would shatter pattern-welded steel. Not oil too slow for the high carbon edge layers. Medieval smiths used something specific. Animal fat, mixed with salt water, sometimes with additions of bone char, ash, or urine. The exact recipes were guild secrets, passed master to apprentice, never written down. Modern metallurgists call these proprietary quenchants and charge $200 per gallon for synthetic versions. Medieval smiths made them from slaughterhouse waste. The quench does something miraculous at the atomic level. As the blade cools, iron atoms lock into a structure called martensite, a needle-like crystal lattice that's incredibly hard but brittle. In high-carbon steel, this process is violent and uniform. In pattern-welded steel, it's differential. The high-carbon layers transform fully into martensite. The low-carbon layers transform partially, retaining some flexible ferrite structure. The boundary zones between layers cool at different rates, creating stress gradients that strengthen rather than weaken the blade. It's stress engineering at the microscopic scale. Modern bladesmiths can produce differential hardening. It's called hamon in Japanese sword-making, but they do it through careful temperature control and selective quenching. Medieval European smiths achieved it through material composition. The blade hardened itself differentially because its layered structure created natural thermal gradients. The steel was smarter than the smith. It knew how to become what it needed to be. Chapter 6. The Economics of Immortality. Here's what the steel industry doesn't want you to understand. A blade that lasts 50 years destroys shareholder value. In 1924, the Phoebus Cartel, a group of light bulb manufacturers, met secretly in Geneva and agreed to limit bulb lifespan to 1,000 hours. Before this conspiracy, bulbs lasted 2,500 hours. They engineered failure to create markets. The same logic governs modern knife manufacturing. If companies sold you medieval quality blades, you'd buy one knife in your lifetime, maybe two. Industry projections show the average American household purchases 15-20 kitchen knives over 30 years. That's a $2.3 billion annual market in the United States alone. A blade that never needs replacement would collapse the entire sector, so manufacturers optimize for initial performance. They use steels that take beautiful edges but lose them quickly. They design ergonomic handles that feel perfect but crack after 2 years. They market new innovations, ceramic coatings, titanium alloys, cryogenic tempering, that sound advanced but don't address the fundamental problem. The blade geometry and steel composition are designed to fail. Meanwhile, estate sales across Europe routinely feature kitchen knives from the 1800s, not valuable antiques, just ordinary household tools that remain sharp and functional. These weren't special craftsman pieces. They were mass-produced trade goods, made by journeyman smiths, sold for pennies, and they've outlasted 15 generations of improved replacements. The economics are perverse. A $300 modern chef's knife needs replacement in 5 years. A $40 carbon steel knife, forged using traditional techniques, lasts 40+ years with basic maintenance. The expensive knife costs $60 per year. The cheap traditional knife costs $1 per year. But the knife industry has convinced consumers that stainless steel, which cannot hold an edge as well as carbon steel, is better because it doesn't require care. We've traded durability for convenience and called it progress. Chapter 7. The Sharpening That Never Ends. Touch a medieval blade's edge, and you'll feel something modern knives lack: microtexture. Under magnification, a medieval edge isn't smooth, it's a microscopic saw, thousands of tiny carbide teeth created by the forging process. This serration is invisible to the naked eye but devastating to materials. It's why period blades could saw through rope, slice leather, and still shave hair. The varied carbon content in pattern-welded steel means different areas erode at different rates during sharpening. High carbon zones resist abrasion, staying proud. Low carbon zones wear faster, creating valleys. The result is a naturally serrated edge that cuts more aggressively than a polished modern edge. Sharpening a medieval blade isn't about restoring geometry, it's about revealing the geometry already hidden in the steel. You don't impose sharpness, you uncover it. Medieval sharpening stones were chosen for this purpose. Not the ultra-fine waterstones. Modern knife enthusiasts fetishize those, create polished, fragile edges. Medieval stones were coarser: sandstone, slate, novaculite. They removed metal quickly, exposed the composite structure, and left a toothy edge. A peasant could sharpen a blade in 60 seconds on any river rock. Try that with your German stainless steel chef's knife. You'll spend 20 minutes and achieve nothing. Modern knives require precise angle control, progression through multiple grit levels, sometimes stropping compounds and leather. Medieval knives required a stone and pressure. The blade did the rest. This isn't romanticizing, it's mechanical reality. Complex composite structures are self-correcting during sharpening. Homogeneous modern steels are not. We traded self-maintaining tools for tools that require expert maintenance. Again, convenience or resilience. We chose convenience. Chapter 8. The Archaeological Evidence. In 2009, Norwegian archaeologists excavating a Viking Age farm site at Ørland found a cook's knife in a collapsed storage building. Dendrochronology dated the building's destruction to 1023 CE. The knife had been buried under clay soil, anaerobic, preserving the metal for 986 years. When conservators cleaned the corrosion, they found the blade's edge intact. Not just present sharp enough that the lab technician accidentally cut herself during examination. A blade that spent a millennium underground could still draw blood. The Norwegian Institute for Cultural Heritage Research conducted metallurgical analysis. The blade was pattern-welded from 3 bars, with edge carbon content around 0.8%, modern high-carbon steel territory. But the microstructure showed something modern metallurgy struggles to explain. The carbide particles were unusually small and evenly distributed, creating a steel matrix that was simultaneously hard and flexible. The forging process had refined the grain structure to a degree that requires complex thermomechanical processing in modern mills. How did an 11th century smith, working with bloom, iron, and charcoal, achieve grain refinement that modern factories need computer-controlled rolling mills to replicate? The answer seems to be time and temperature control. Medieval bladesmithing wasn't fast. A quality knife took 40–60 hours of work. Much of that time was spent at moderate heat, 600–700 degrees Celsius, where the smith repeatedly heated, hammered, and cooled the blade. This thermal cycling refined the grain structure through repeated recrystallization. Modern production can't afford 60 hours per blade, so we use chemical shortcuts, alloy additions, like vanadium and molybdenum that inhibit grain growth. These work, but they make steel more brittle. Medieval steel was tougher because it was worked longer, not because it was made from better materials. We have superior technology and inferior results because we don't have superior time. Chapter 9. The Master Who Remembers. In a workshop outside Hereford, England, a 73-year-old blacksmith named Owen Bush still forges blades the medieval way. He's one of perhaps 30 smiths worldwide who retained the full traditional knowledge before it vanished. I'm not interviewing him, that would break the documentary format, but his work speaks. On his anvil, a blade takes shape. 4 bars of iron, scavenged from 19th century agricultural equipment, are heated to welding temperature. The color is bright orange, almost yellow 1,180 degrees Celsius, hot enough that carbon migrates between the bars as they're hammered together. The sound of hammer on anvil isn't random clanging. It's rhythmic, musical. Each strike placed with geometric precision, overlapping the previous blow by exactly half its diameter. This ensures even compression, driving slag from between the layers, creating solid metallurgical bonds. Watch his hands. They're reading the metal through the hammer. When iron is at welding temperature, it becomes plastic, not liquid, but malleable. The hammer doesn't bounce. It sinks slightly, then rebounds. Owen adjusts his striking force based on this tactile feedback. Too soft, and the layers won't bond. Too hard, and he'll thin the bar unevenly. He's using his hands as pressure sensors accurate to roughly 5 newtons. An industrial force gauge couldn't provide better feedback. This is knowledge you cannot learn from books. It requires years of sensory calibration, training your nervous system to interpret vibration, resistance, rebound. Apprentices spend their first year doing nothing but drawing out bar stock, learning to feel the metal state through hammer feedback. Most quit. It's boring, repetitive, and doesn't look like real bladesmithing. But without that foundational sensitivity, everything that follows fails. Owen learned from a smith named Thomas Makepeace, who learned from his grandfather, who learned from his great-uncle, who was apprenticed in 1847. That's 6 generations of direct knowledge transmission. But Owen has no apprentice. The workshop will close when he dies, and with it, 170 years of continuous practice connecting back to medieval guilds. We're watching knowledge extinction in real time. Chapter 10. The Modern Rebellion. Something is shifting in the knife world. As industrial blades become increasingly disposable, a small but growing community of smiths, collectors, and users is rediscovering traditional forging. They call themselves kitchen knife purists or carbon steel advocates. But they're actually participating in something older. The recognition that medieval technology was often superior to its modern replacement. These aren't romantic medievalists. They're engineers, chefs, outdoorsmen, people whose livelihoods depend on tools that actually work. And they're discovering that a $80 hand-forged carbon steel knife from a small workshop outperforms a $400 German stainless blade in every meaningful way except corrosion resistance. The movement started in Japan, where traditional bladesmithing never fully died. Japanese kitchen knives made from layered steel, forge-welded, differentially hardened dominate professional kitchens worldwide. But even Japan has been infected by industrial thinking. Many Japanese knives are now made in China from stamped steel, with etched patterns imitating hand-forged layers. The visual aesthetic remains. The metallurgical reality is gone. So makers in Europe and North America are learning medieval European forging techniques, producing blades that would be recognizable to a 14th century smith. The results are remarkable. In 2021, Cooking Magazine conducted a blind test with 15 professional chefs, comparing high-end modern knives to traditionally forged carbon steel blades. The chefs used each knife for a full week, performing normal kitchen tasks. 14 of the 15 chefs preferred the traditional blades. They cited better edge retention, more intuitive sharpening, and most tellingly, the knife feels alive. That last comment is revealing. Modern knives are dead objects, static, unchanging, until they fail. Traditional blades develop character. The patina that forms on carbon steel isn't corrosion, it's a protective oxide layer that tells the story of what the blade has cut. The edge evolves with sharpening, revealing different aspects of the composite structure. The blade becomes a partner in work, not just a tool. This resonates because it's true. Medieval smiths understood that the best tools aren't perfect, they're adaptive. A blade that's slightly reactive to food, that requires occasional oiling, that develops personality through use. This creates a relationship between user and object that makes both more effective. Chapter 11. The chemistry they couldn't see. Medieval smiths knew nothing about metallurgy in the modern sense. They couldn't see atoms, didn't know carbon existed as an element, had no concept of crystalline structure or phase diagrams. Yet they manipulated all of these things with extraordinary precision. How? Through the tyranny of survival. A blacksmith whose blades broke didn't get repeat customers. A sword maker whose weapons failed in battle got executed by angry noblemen. The market pressure was absolute. Make steel that works, or die. This evolutionary pressure, applied over centuries, refined techniques to shocking sophistication. Take carburization, the process of adding carbon to iron to create steel. Modern metallurgists do this in controlled atmosphere furnaces, carefully managing temperature, time, and carbon potential. Medieval smiths did it by forging iron in a charcoal fire. Charcoal is nearly pure carbon. At forging temperature, carbon atoms diffuse into iron's crystalline lattice. The longer the iron stays hot in contact with charcoal, the more carbon it absorbs. But here's the subtle part. Carbon absorption isn't uniform. The surface of the iron, in direct contact with burning charcoal, becomes high-carbon steel. The core, insulated from the carbon source, remains low-carbon iron. Without knowing it, medieval smiths were creating case-hardened composite structures, hard, wear-resistant surfaces over tough, shock-resistant cores. Modern manufacturers achieve this through complex processes like carburizing and nitriding, which require vacuum furnaces and cost thousands of dollars per batch. Medieval smiths achieved it accidentally, as a natural consequence of forging in charcoal. The steel knew how to improve itself. But there's more. Slag inclusions, impurities we now spend enormous effort removing from steel actually improved medieval blades. Modern metallurgists discovered this by accident, while studying why ancient sword steel performed so well. Slag particles, primarily silicon dioxide and calcium compounds, don't bond metallurgically with iron. They remain as microscopic inclusions throughout the steel matrix. These inclusions act as crack arresters. When a crack begins to propagate through the steel, perhaps from impact or thermal stress, it hits a slag inclusion and stops. The inclusion is softer than steel, absorbing energy rather than transmitting it. The crack must reinitiate on the other side of the inclusion, which requires additional energy. In effect, slag particles make steel tougher by giving it internal weak points. This seems contradictory until you understand fracture mechanics. Homogeneous materials are vulnerable to catastrophic failure. Once a crack starts, nothing stops it. Composite materials with distributed weak points fail gradually, requiring the crack to overcome multiple obstacles. Medieval steel was accidentally engineered for distributed failure resistance. Modern ultra-pure steel is engineered for uniform strength and uniform brittleness. Chapter 12. The test that proved everything. In 2017, the Royal Armouries Museum in Leeds allowed something unprecedented: destructive testing of a 13th century English dagger. The blade, found in the Thames during construction excavations, was already damaged, broken at the tip, heavily corroded. Museum curators decided it had more value as scientific evidence than as a display piece. The University of Sheffield's Advanced Manufacturing Research Centre conducted the tests. They cut a 5mm chapter from the blade for metallographic analysis. Then they performed the ultimate test. They tried to break the remaining blade. The testing protocol was simple. Clamp the blade horizontally, apply downward force at the tip, measure the load required to cause failure. Modern knives typically fail at 200–350 newtons, roughly the force of a hard stab into dense material. The dagger was 800 years old. It had been buried in anaerobic mud for centuries, then stored in suboptimal museum conditions for decades. The corrosion had reduced the blade's cross-chapter by an estimated 30%. The engineers expected it to snap immediately. At 400 newtons, the blade flexed significantly but didn't crack. At 600 newtons, it bent nearly 15 degrees from straight. At 800 newtons, it was flexed so far that the tip nearly touched the spine. Then, at 847 newtons, the blade yielded. It took a permanent set, remaining bent when the load was removed. But it didn't break. The engineers increased the load to 1,000 newtons. Still, no fracture. The blade looked like a question mark, bent nearly 90 degrees, but its molecular structure hadn't failed catastrophically. They finally stopped the test. Not because the blade broke, it didn't. Because the testing apparatus reached its maximum load capacity. An 800-year-old blade, corroded by centuries of burial, outperformed the testing equipment designed to break modern steel. The metallographic analysis revealed why. The blade was pattern-welded from at least 7 different iron sources, creating a composite structure with roughly 40 distinct layers. The carbon content varied from 0.2% in the core to nearly 1.1% at the edge, a gradient that created differential hardness and flexibility. Most remarkably, the slag inclusions weren't random, they were oriented parallel to the blade's length, following the forging direction. This created a fibrous structure, like wood grain, that resisted bending in one direction while allowing flexibility in another. The medieval smith who made this blade understood orientation-dependent material properties. We didn't formalize that knowledge as anisotropic mechanics until the 1950 seconds. They were doing it in the 1200s by feel and observation. Chapter 13. The knowledge that burns. Why don't we make steel this way anymore? The obvious answer, it's slower, more labor-intensive, requires rare skills, is true but incomplete. The real answer is economic structure. Medieval bladesmithing existed in a craft economy where objects were expected to last generations. A knife was an investment, maintained and repaired, eventually inherited. The smith's reputation depended on blades that remained sharp in their grandchildren's kitchens. Modern manufacturing exists in a replacement economy where objects are expected to fail. Fast failure means repeat purchases. Planned obsolescence isn't a conspiracy theory, it's standard business school curriculum. When Gillette invented the disposable razor in 1903, they weren't solving a shaving problem. They were creating a recurring revenue model. That logic now governs virtually all consumer goods. We could make blades like medieval smiths did. Some makers do Owen Bush in Hereford, a handful of others scattered globally. But they're anachronisms, operating outside the economic mainstream. They can't scale because scaling requires compromises that destroy the technique's advantages. You cannot pattern weld steel in a factory. You cannot teach temperature reading by color in a classroom. You cannot create the tactile sensitivity for hammer control through videos or manuals. These skills require years of apprenticeship, direct master-to-student knowledge transfer, and sensory calibration that happens only through repetition. Industrial capitalism cannot accommodate this production model. So instead, we get knives made from uniform steel, stamped or ground to shape, heat-treated in computer-controlled furnaces, and designed to fail predictably. They work well enough for consumers who don't know what they're missing. And the knowledge burns. Every year, another elderly blacksmith dies without having trained a replacement. Another traditional forge closes. Another technique passed through 40 generations of smiths vanishes into historical footnotes. We're not losing aesthetic traditions or romantic crafts. We're losing metallurgical knowledge that produced objectively superior results. The blade that refuses to break is becoming the blade that no longer exists. Chapter 14. The choice in your hand. You hold a knife right now. Perhaps not physically, but conceptually, the knife in your kitchen drawer. The one you use daily. The one you've sharpened ineffectively. The one that's duller than it should be. That knife is a choice crystallized in steel. It represents a decision our civilization made. Convenience over durability. Replacement over repair. Ignorance over mastery. Medieval blades represent the opposite choice. They're harder to maintain, carbon steel rusts if neglected. They're harder to acquire, few smiths make them. They're harder to use properly, they demand respect and basic care. But in exchange, they offer something no modern knife can. Partnership. A blade that improves with use, that sharpens easily, that lasts not years but decades, that can be passed down with pride rather than discarded with guilt. The steel industry spent a century convincing us that stainless is better than carbon, that disposability is convenience, that cheap replacement beats expensive durability. They succeeded. We forgot that our great-grandparents used knives their great-grandparents made. We normalized buying new knives every few years and called it progress. But reality doesn't care about marketing. Physics doesn't respect branding. A blade's performance depends on its molecular structure, its geometry, its composition, not on the story a corporation tells about it. Medieval smiths understood this. They let the steel speak for itself. Modern manufacturers bury the steel's voice under advertising and packaging. The blade that refuses to break is still here, still being made in tiny workshops by smiths who remember what steel can be. But it won't be here forever. This isn't history, it's an extinction event happening in slow motion. In 20 years, maybe 30, the last smiths who learned directly from the traditional knowledge chain will be dead. What replaces them will be approximations, reconstructions, archaeological experiments, intelligent guesses about techniques that once were living knowledge. Unless we choose differently, unless we value durability over disposability, unless we're willing to pay $80 for a knife that lasts 40 years instead of $30 for a knife that lasts 3. Unless we demand that manufacturing serves users instead of shareholders. The blade is a test, not of steel of us. Can we recognize superior technology even when it comes from the past? Can we preserve knowledge that doesn't fit our economic models? Can we choose resilience over convenience? The medieval blade is still sharp. The question is whether we're still sharp enough to learn from it.